Hi there, welcome to the pGrid introduction. We hopefully will be able to explain to you how pGrid can help you get to know your grid. It's a short presentation, but it's still sort of 15 minutes, and here we go. First of all, I want to explain what we mean by grid in pGrid. Grids connect producers of power generators to consumers, and they have to balance these two things every second of every day. With pGrid, we consider a grid to be any size really, from national grids, regional distribution grids, regional energy systems, local energy systems, villages, etc. We can model any of those as autonomous standalone balancing grids. We're just looking to balance the power on the grid, looking at load level, which we'll look at in a minute. And we assume that there are sufficient wires around, distribution wires and transmission wires and assets, to be able to allow the generation and the demand to interact. That's an assumption, not always true, but it is an assumption that we take in pGrid to do this analysis. And what you've got with pGrid is basically an easy to use web-based tool designed to make the complex world a bit simpler. And we really targeted this for anyone with interest in how to transition to net zero should be able to use and to look at pGrid and understand what's going on. So the agenda for this presentation, we're going to show you how pGrid works. We're going to talk about the load level on the system. Basically, pGrid takes any grid system and asks itself the question, what load is on the system and how can we balance that load with generation. We're going to specifically look at an assumption behind the availability of nuclear power assets in the scenario we're going to look at. Basically trying to explain to you that pGrid is a bit like a Rubik's Cube. We're given by people like the National Grid Future Energy System scenarios. We're given data, we're given output data, we're given the number of generators, this kind of thing, but they don't show us the detail behind that. So we can use pGrid as like a Rubik's Cube to try different assumptions within pGrids to get all the colours to line up in a way that doesn't break the boundaries that are set by the published scenario itself. We're then going to go on and look at a scenario which is the consumer transformation scenario from the National Grid under their Future Energy Scenarios programme. And basically what you do with pGrid is you become the system operator. You say, well, I'm the system operator in this world. What do I do? I'm balancing generation and supply, and can I prove to myself that we've got a system where the lights will stay on? And we're actually going to show you that currently we think maybe they don't stay on in this scenario, but we'll explain to you that we don't really think that. We're just trying to understand what the future energy scenario team must be thinking in order to make it all work. And we're going to learn from pGrid a little bit about how the future energy scenario works in detail and get behind some of the assumptions that they must be making but don't necessarily publish. So we're going to have a look at the nuts and bolts of pGrid here. This is really a chart that shows what's going on in pGrid to give us the answers to the questions we've got. And it's all based around this concept of load level. How many megawatts is on the system at any point in time, and how does the generation assets that we've got and the storage assets that we've got meet that load level? So we have basically within pGrid the ability to make that question quite simple by considering load to be just one level of load here, a single tranche of load, or over here where we might say there's 10 different levels of load within the year, or 100 levels of load within the year. And these are basically things called duration curves. It's all the same data here. This point here says, okay, we've just assumed that there's the same level of load throughout the year in 2050, that there's no difference between night and day, summer and winter, weekends, business days, etc. And if it was just one level of load for the year, it would need 84 megawatts, that is. And that 84 megawatts would run all year long and produce, in fact, the amount of energy that we actually need in the year. And that energy would be provided by the generating assets that we've assumed, their capacities and their availabilities. And we would order them in their cost, in order of increasing cost. So the cheapest guys go first, the most expensive guys go last, and that way consumers get the cheapest cost of energy. This guy down here is the lowest cost plant we have, which is the nuclear plant, and the one above it happens to be solar, and this one here is the large amount of wind that FES have assumed for this scenario. But we kind of know that load is not the same. throughout the year. It varies, and so what we do is to create these duration curves, is to say, okay, let's just take all these half hours of load and stack them up in 10 equal piles and order those piles in order of load. So this is the pile with the largest amount of load in, half hours with the largest amount of load in, and this is the pile with half hours with the least amount of load in. And when we do that, we start to see some stuff. So we see that the nuclear plant that we've got assumed to be running base load also runs kind of the same amount in every tranche, but the solar plant is starting to show how the shape of solar is coming through on different load levels, and also the wind is also coming through at different load levels. If we then go up a notch and say, well, we really want to get a lot of data and look in real detail, we go to the 100 load levels, the centiles, and these columns here are exactly the same as these columns here, exactly the same as these columns here. They're just taking, instead of 1 pile or 10 piles, 100 equal piles of half hours organized in load level. And this really is what pGrid is doing to help us understand what's going on in the grid. Now, we said we'd have a little look at sort of that nuclear plant, and we saw the nuclear plant earlier, and the nuclear plant has an availability. That availability is applied to the capacity that's put in the system, and basically we've got here a little graph just to show you how we reference data to help us understand a little bit what's going on. So the black line there is the assumption we've used for 2050, and the blue line there, or the green line, is the assumption we had in 2019, just as a reference, just to compare. So they're quite different. The black line is basically calculated by us from what the scenario team at FES told us, which is we have a nuclear power station, it runs so many megawatts and produces so many megawatt hours in the year, so that gives us the ability to work out what its availability must have been. We don't know how it shapes, so we've just assumed it's the same throughout the year. The 2019 curve is what Elexon actually told us nuclear was in 2019. So that's what the nuclear fleet in the UK did in 2019. So a couple of things. One, should we have a shape to availability for nuclear? Maybe we should. And the FES team have clearly assumed that the nuclear fleet is going to be far more available in the future than it is today. So we've learned something from pGrid about what they're thinking. We're going to now look at the actual tool itself in real time. We've taken the screenshots so that the presentation flow is a bit neater, but these are all from the web. As I said at the beginning, this is a web-enabled tool that you can use with your own logins. Also, a feature of pGrid is that we can clone any study. So, for example, the numbers we're looking at my analysis of the Consumer Transformation 2050 scenario, you could take a clone of that for yourself and then just simply start playing with it and put your own data in and your own assumptions to see how your Rubik's Cube, if you like, works out. For those people that don't know what the future energy scenario for consumer transformation is, it basically is a scenario in 2050 where the net zero target is met. It has a lot of electric heat pumps in there, it has a lot of electric vehicles in there, it assumes the world gets very energy efficient, and there's a lot of smart controlled devices. I'm not going to repeat that work here. It's all available on the National Grid website. We've not changed any of it. All of the boundaries that they've set us by giving us their scenario outputs have been met pretty much in this analysis. In other words, the Rubik's Cube kind of does line up. And we're not changing that in any way. So this is the sort of front end of pGrid. Just wanted to show you this really to look at the three things. Top left hand corner, every user has their own set of data, their own Rubik's Cube. So we can provide this Rubik's Cube to anybody that wishes to have their own go at trying to align all of the data. In the bottom right hand corner, it kind of at a primary level tells you whether this scenario works or not, and it's suggesting that this one doesn't. In other words, that the lights probably in this scenario would not stay on. As I said, we're not really saying that National Grid have got a scenario that doesn't work. We're saying that we haven't yet been able to make it work within pGrid, keeping all of their boundaries in place and applying the laws of physics. The multicolored thing here. It gives you a little bit of understanding of what pGrid can do. So the grid scope is what grid are you talking about? We're talking about here the whole of the UK total demand. We produce the demand from our own demand forecasting tool within pGrid called Village 100. Don't have a chance to talk about that on a short presentation like this. We're looking at 2050 and we're looking at a scenario which is a consumer transformation scenario within that, and that's really what we can do. We're going to look at it at a centile level, so we're looking at the detailed level, 100 tranches. There is another resolution which is you can set the number of generators that you want to see in all of the reports. If you load pGrid up with 1,000 solar plants, do you really want to see analysis of all 1,000 solar plants? Probably not. So you aggregate them all up into one line of all of the solar plants, and you can set that level from 10 gigawatts down to 100 megawatts. pGrid needs demand data. As I said, we created this demand data within pGrid. pGrid likes references, so this black line is the reference. This is the 2019 data set that was the actual demand duration curve for 2019. So on the left hand edge we have the highest level of demand, the 100th centile, and on the right hand end we have the lowest level of demand, the first tranche. The red line is what Fez told us the consumer view would be, created by pGrid, but at the right level of load. And the green line is actually the load on the system that Fez told us was in their scenario. And there's quite a big difference, not only between what happened in 2019 and what's going on with consumers in 2050, but also the difference between what consumers use in electricity and the amount of electricity that's needed by the system. And the difference between these two we'll see is electrolysis and exports that Fez have assumed. So alongside the demand assumption we've taken from Fez, we need their generation assumption, their installed capacity. And this is what we have in this chart. This is all the capacity that they've assumed in their system. And here is our nuclear power station that we're taking a look at. And they told us that there was nearly 16 gigawatts of nuclear available. And they told us that it was going to run at around 101, 102 terawatt hours. And we worked out that that was an availability of 74%. We've just put the installed capacity in order of merit, in order of the bid price that we expect these assets to run at. And as you can see, we've got a lot of plant here with very, very low marginal bid prices. It's going to be a very low price system. We're not looking at prices in this analysis, we don't have enough time, but pGrid has worked out prices and profits for all of these generation assets. Really that's it. pGrid works in half hours. You can always look at data in half hours. This is a business day in April in 2050. This is actually just a graph of the load level. And so you see the numbers, the tranche numbers along the top. And this was an analysis where we used deciles, so 10 levels of load. And it just happens to be a day where you've got the lowest level of load in the middle of the night, in the early morning, and the highest level of load in the middle of the day. And it shows you what's going on. And you can run this for any day of any month, weekend or weekday. We can produce prices from this because we know what the prices are in each of these load levels, and so you could reproduce a curve that shows you how prices change within this scenario. Again, we don't have enough time in this presentation to go into prices, but that is all within pGrid. So back to this centiles analysis that we're looking at. This is the same graph as we saw earlier when we were talking about the single tranche, the deciles and the centiles. We are going to just have a look at tranche 36. There it is, sort of stuffed below that green arrow. We're going to take a detailed look at what's going on in tranche 36. So this is highlighted tranche 30. So this is just a list of all the 100 tranches in this analysis. So that graph was produced from this data, but it just gives you a little bit more information as to what's going on. So this is tranche 36. The system state is that there's a storage call, and there's a storage call because the plant margin is minus 1%. So there's insufficient plant available, generating plant available to meet demand, and so the system says, right, I'm going to need storage to help me out here. So it goes to the storage assets. It says, look, I'm looking for 4.5 gigawatts of power in this tranche in order to get a sensible plant margin. And so the storage assets discharge what they can, but unfortunately they can't discharge to 4.5 gigawatts. They come back and say, well, there's 2.3 gigawatts of residual that we can't store. And we haven't really got time to look at storage in detail on this presentation, but we can show you how we've analysed storage and how that residual amount is calculated. But that ends up with an energy systems operator margin of 2%, which we consider to be unstable. We consider 5% to be stable, and so the system is unstable, and we think the lights have probably gone out. So looking at tranche 36 in some detail here, this is tranche 36. What went into producing those answers for this load level at 72 gigawatts and 536 megawatts. That's the load level on our load chart, duration chart. So what we do is we put the power stations that we have in the model in order of their bid price, and we start with the cheapest, which is our friend the nuclear power station. The nuclear power station has said, I really want to run all the time, so I'm going to bid a negative bid price. I just want to always be dispatched as the first ranked in merit plant. We needed 72 gigawatts. The nuclear power station has 15 gigawatts, 16 gigawatts, but only 11.6 gigawatts are available to this tranche because of availability. So we put the nuclear power station in, and our cumulative stack capacity goes to 11 gigawatts, and the imbalance goes down by 11 gigawatts. And we just keep adding the plants in order of merit. And what happens is the stack capacity rises, or if you like, the imbalance decreases. These are two sides of the same coin, until we reach the hydrogen plant at the top, which is the last bit of plant we have available in the model, or in this scenario as shown to us by Fez. And when we add the hydrogen plant in, we get a cumulative capacity of 71 gigawatts, but we needed 72, so we still have an imbalance of 908. And this is really just showing you how we produce these analysis in each of the tranches. And so we have a shortage here, and the only thing the energy system operator could do at this point is ask for some help from the storage assets that it has. So this is looking at the 100 centiles, and it's looking at net margin, and net margin is the red line. And what we mean by net margin is, right, let's have a look at each tranche as what the load level is, what is demand, and we have our lowest demand on the right and our highest demand on the left. And what is the plant available to meet that demand, which is this lightish blue color here. What's available to meet demand? So at low levels of demand, we have a lot of available plant margin, a lot of renewable energy on the system that we don't need. And where we don't need it, where it's in excess of the load on the system, we have this free energy, renewable energy that otherwise we'd have to turn the windmill off or put a blanket over the solar panel, if you will. So no, we don't do that. The energy system operator says, I'm going to put that into storage. So this is where we're able to take free energy and put it into storage, this dark green bar. And the opposite of that is where the net margin is very low, we go to storage and say, can you help us out and can you deliver some energy back to us? And that's these yellow periods. And in tranche 36, we saw that there was a storage call. So as energy system operator, we're looking at that saying we really want the lights to stay on. So we want that net margin to stay above 5%. And so we can see that in tranche 36 and other tranches, that isn't the case. And so we'd need to go back, and within the boundaries of pGrid and within the boundaries that Fez have set, how can we make that net margin any larger? And the only option to us would be to move some demand around to reduce the load in that tranche 36 and the other tranches where net margin is low. So we have these boundaries that are set by Fez, giving us some sort of answers to the question. And they said, well, we'll tell you that nuclear ran for 101 terawatt hours in our model, and we've now got nuclear running at 102 terawatt hours in our model. So we're kind of pretty happy with that. That's where pGrid goes, do you know what, that's pretty good. Obviously nuclear runs base load, so that's maybe a little bit easy to do, but we're getting that for all of the plant in the system really. We've got wind running at 106 versus 108, offshore wind 308, same as 308. A lot of these numbers are very, very compatible. Solar is pretty much bang on, 65 terawatt hours in pGrid, 65 terawatt hours in the FES 2050 consumer transformation scenario. So we have a few differences, and this is where we're kind of scratching our head and thinking about what assumptions they may be taking. And so this is where we go on to do a bit more work. So again, boundaries set by the FES consumer transformation. These are the numbers they told us for agriculture, industry, transport, SME, etc. And they said, okay, we've got demand at 451 terawatt hours. Well, great, we've managed to model that also to 452 terawatt hours. Fine, carry on. And we talked about this big difference between consumers' use of electricity and the system's need to produce it. The 745, they had 741, again, pretty happy with that. The difference between the consumer use of electricity and the system level of load for the year is that they have a lot of electrolysis creating hydrogen. We have losses on the system, and they have a lot of exports where we have a lot of excess renewable energy. Then this is exported to other countries, and this is considered as part of demand. So we don't have it in our green bars for the net margin. This is what we've assumed is being exported in each half hour added up. This is the figures for the whole year. So we're just going to end on this chart, which is net zero. So this scenario from National Grid Future Energy Scenarios Consumer Transformation said it was a net zero compliant scenario. And we see that here because they've got the zero. There is no carbon being emitted from their system. They have the electricity part of it, sort of reducing carbon, abating carbon, capturing carbon and storing it, of 52 million tonnes of carbon dioxide equivalent, and they have some production. So the net of that is 49. We've got 41, so maybe some work needed here. But we know that the amount of capacity that we have for BECCS is correct, and we know that we've pretty much got it running the number of gigawatt hours. There was a little bit of work to be done there. Probably it's this number here that we need to have a think about, which is our assumption for how many kilograms of carbon are removed for every kilowatt hour of electricity generated by this generation type. This is a complicated area. We'll do a little bit of work on that. A little change to that will bring our 41 in line with their 49. So this is really just showing you again that this idea that we're working with references, with the boundaries that we have from their output that they've told us about their scenario, and trying to think about what we need to assume to get the same result. So that's the presentation for today. It's a very summary level. We haven't talked about storage, which we do have within pGrid. We haven't talked about Village 100, which is a detailed demand forecasting tool to produce those duration curve numbers. Please contact us under these details, and we're very happy to give you a full demonstration of what pGrid is capable of doing. Thank you very much for watching.